Welcome to the cloud computing tutorial. Today we are going to discuss about the roots of cloud computing. So we can track the roots of cloud computing by observing the advancements of several technologies. So especially in hardware related to your virtualization, multi-core chips. Next, second one is internet technologies, web services, service-oriented architecture, Web 2.0. Third one is distributed computing, that is clusters, grids, and fourth one is systems management, autonomic computing, data center automation. So next we'll see the figure that shows the convergence of technology fields that significantly advanced and contributed to the advancement of cloud computing. So this is the figure. So as we see in the previous slide, these are the four components that leads to the development of the cloud computing. Before cloud computing, these are the technologies are existed: hardware virtualization, multi-core chips, service-oriented architecture, web services mashups, Web 2.0, and third one is autonomic computing, data center automation. Next one is utility and grid computing. So let us see one by one. First one is the mainframes. So what is mainframes? So what are the changes has been occurred right from the mainframes to clouds? So first we'll see the definition of mainframes. Mainframes are high performance computers with large amount of memory and the data processor, so that process the billions of simple calculations and transactions in real time. So mainframes are the high performance computers which have the capacity of performing the large instructions and the transactions in a less time, in a real time. So that is the definition of the mainframe. So from mainframe to cloud. So mainframe era collapsed with the advent of fast and inexpensive microprocessors, and IT data centers moved to the collection of commodity servers. So commodity servers, so commodity means the less expensive. So we can get the servers with a minimal cost. So apart from its advantage of the mainframe, the new model which is unavoidable leads to the isolation of workload into dedicated servers. So mainly due to the incompatibilities between the software stacks and the operating system. So in addition to the unavailability of efficient computer networks means that IT infrastructure should be hosted in proximity to where it would be consumed. Altogether, these facts have prevented the utility computing reality of taking place on modern computer system. So the mainframe era collapsed by introducing the advancement of inexpensive microprocessor, and the IT data centers moved to the collection of commodity servers. So the mainframe era has been collapsed by introducing the inexpensive microprocessors and the IT data centers. So these are the figures of the mainframe computers. So for example, we have kept here mainframes computer before the cloud computing. Second technology, web service. Web service is a standardized method for propagating messages between client and server applications on the World Wide Web. So we can exchange the messages between the client and server applications through the internet. So web service is a software module. The purpose is to accomplish a specific task. Next, coming to the service oriented architecture. So service oriented architecture is a design pattern which is used to build the distributed systems. So these systems will deliver services to the other applications through the protocol. So coming to the components of this web service, so these are the various things we consider. Web service integration. Web service standards enable applications on different platforms to interoperate seamlessly. Second thing is service oriented architecture. So as we see in the previous case, service oriented architecture here, so is a design pattern used to build the distributed systems for delivering the services to the other applications with the help of the protocol. So it is well defined and independent services to perform the business functions. Next, service accessibility. So matured web service allow on-demand access to powerful services with the help of the interfaces accessible by other services. Consumer web and web 2.0, programmatically combining services, so that became popular, leveraging public APIs from major providers. Next, coming to the software as a service. So cloud applications are composed of reusable services, so that enhancing business solutions. Coming to the public marketplaces, repositories like programmable web and app exchange, so that will list thousands of APIs and mashups for creating innovative solutions. Next technology is grid computing. So first we'll see the definition of the grid computing. So grid computing is nothing but a distributed architecture that combines computer resources from different locations to achieve the common goal, that is to achieve the common task, to fulfill the particular task. This grid computing enables aggregation of distributed resources from the different places and transparently access them. Some examples we consider: TerraGrid and EGE, so seeks to share compute and storage resources. These are distributed across different administrative domains with their main focus is speed up a broad range of applications such as climate modeling, drug design, and protein analysis. So these are the common applications to perform with the help of the grid computing. Next, the drawback here in grid computing is lack of performance isolation in grid computing. So that is, the activities of one user or the virtual organization will impact the performance by the other users sharing the same resources. That is particularly problematic in environments where the resources are oversubscribed or when users do not cooperate efficiently. For example, let us take the example. If one user consumes large amount of computing power or storage, so this will reduce the availability of resources for others. So they has to be in an ideal state. So this leads to the delay in their performance as well as throughput. So it degrades the performance for all users involving in the sharing of resources. So this issue is especially in critical for applications which involves require time delay execution, such as those with strict deadlines or real-time processing needs. So coming to the second drawback, so it leads to the frustration when using grids is the availability of resources with diverse software configurations including disparate operating system, libraries, compilers, runtime environments, and so on. So incompatibility will be there. when several users are sharing their resources. For example, one user is using the Windows operating system, other user using some other operating system, that is the computing power will be different, so this leads to the incompatibility. These two are the major drawbacks in the grid computing. Coming to the utility computing, so as grid computing becomes the more popular, large grid installation experiences the new challenges, so such as sudden surges in resource demands, that is increasing the demand in terms of the resource capacity. So in such cases, additionally user has to engage more resources, such as manipulating resource allocation to their advantage, further complicating resource management and fair distribution, that is the allocation of resources to the all users in equal manner. So for ensuring all these things, in utility computing environments, users assign utility value to their jobs. So this utility value assigning should be done based on the quality of service constraints like deadlines and importance of the task. That is the task deadlines or importance of the task. So this utility value represents low much they are willing to pay to meet their demands. Service providers aim to maximize their own utility, often equating it with profit. So they may prioritize the jobs with a high priority per unit of resources. So the task will be categorized with respect to high priority task or low priority task. So the low priority task will be executed prior and followed by the high priority task will be executed followed by the low priority task. So the resources will be allocated based on the priority of the task. Next, coming to the hardware virtualization. So this hardware virtualization can be considered perfect fit for overcome the most operational issues with respect to the data center building and maintenance. So the hardware virtualization allows running multiple operating systems and software stacks on a single physical platform. So consider the diagram here. So is a software layer, virtual machine, monitor or hypervisor. So the responsibility or the objective of the hypervisor is allow multiple machines on a single physical host. So if you look at the diagram here, virtual machine 1, this virtual machine 1 may consist different components: hard user software, email server, database, web server. Similarly, virtual machine 2, virtual machine 3 and so on. So all these multiple machines are running on the single physical host, so that is the hypervisor. So this hypervisor mediates access to the physical hardware representing each guest operating system. So this is the one guest operating system, this is another guest operating system, this is another guest operating system, that is virtual machine, which is a set of virtual platform interfaces. The number of virtual machine monitor platforms exist that are based on the mini utility or cloud computing environment. So coming to the examples of the hypervisors: virtual machine, VMware ESXi or Xen hypervisor or kernel based virtual machine. First we'll see VMware hypervisor. So is a pioneer in the virtualization market. Its ecosystem of tools ranges from server and the desktop virtualization to high-level management tools. Second one is the Xen hypervisor. So it started as an open source project and has served as a base to other virtualization products, both commercial and open source. It has pioneered the para virtualization concept on which guest operating system, that is by means of specialized kernel, and it can interact with the hypervisor. Next, third hypervisor is kernel based virtual machine hypervisor. Is a Linux based virtualization subsystem, and it has been part of the mainline Linux kernel since 2.6.20 version. Coming to the last one, virtual appliances and open virtualization format. First, we'll talk about what is the virtual appliances. So if an application combined with an environment, so which is needed to run it, operating system, libraries, compilers, databases, application containers, and so on. All these are the required component to run an application. So all together we call it as a virtual appliances. So packaging application environments in the shape of virtual appliances, which eases software customization, configuration, and patching, which improves the portability. So most commonly, an application is shaped as a virtual machine, a disk image which is associated with the hardware requirements, and it can be readily deployed in a hypervisor. So it aims at open, secure, portable, efficient, and extensible. The next component is open virtualization format. So this open virtualization format package consists of a file, set of files describing the virtual machine hardware characteristics. Those are the memory, network cards, and disk. Coming to next one, operating system details, startup and shutdown action, and virtual disk themselves. So all these are the components which are existed in a open virtual formats. Last one is autonomic computing. So the increasing complexity of computing systems has motivated research on autonomic computing, so that is which seeks to improve the systems by decreasing the human involvement in their operation, that is development of the systems by increasing the human involvement. So the systems should manage themselves. Systems should be designed in such a way that they can operate on their own, so with high level guidance from the humans. The large data centers of cloud computing providers must be managed in an efficient way. So in this sense, the concept of autonomic computing inspire software technologies for data center automation. So all these are the roots of the cloud computing.